Okay, let's get going. First, before we talk more about missing data and multiple imputation, I want to talk about the homework for today. So the first question is about the response by John Huber to the presentation that McCartan Humphreys and Alan Jacobs gave about their paper at Columbia a few months after it was published. And, you know, as you're probably aware, this is the last official lecture. So ostensibly, you need to know a lot of things. And one of the things that you're going to encounter is you go out and start to try to use a Bayesian approach, whether it's exactly the one outlined by Humphreys and Jacobs or not, is that when other people read, you know, your results and whatnot, you're going to encounter a fairly toxic combination of confusion and skepticism. That is exemplified by John Huber's response. Of course, he prefaced his remarks at the beginning by saying he didn't really know much about what was going on. But he does know a lot about the practice of political science research and how something like this would fit in and be received and what would be the challenges involved with that. So let's talk about what it is he actually said, and then talk about how you think someone like, you know, McCartan would have responded if there had been, you know, more time and didn't have to get to everyone's questions and stuff like that. So what were the main things that Huber was saying?
So I think the main criticism was raised against the difficulty of setting convincing priors. He basically said that I think he said something like, "Oh, you're gonna have a hard time doing this in a convincing way," and potentially the response to that is that the reason for priors is not to do it, let's say, in a way that everybody is convinced and everybody buys it, but like in that pure way to make sure that the reader is aware of the thought process behind it and saying, these are what my beliefs are, and let's say the compromise between my beliefs and the actual data is the results I'm giving you. And of course, the priors are completely subjective and can potentially be changed from a research to another about the same topic if the authors disagree on what is a valid prior.
Good. What else?
Bad at catching things, but I got that. He also said that like the typical approach is to basically like assume that your priors are true given certain information, but he also proposed this like alternative emphasis within the framework whereby you would have to define and determine what you would have to believe in order to be convinced of a causal effect when presented with new evidence.
Right. So a little bit of turning around the question. I don't think if you're doing the analysis, you want to completely substitute that. But in addition to your sort of main results, where you might say, okay, this is what I believe, you could also have, like, for the benefit of everyone who might be reading your results, okay, like if your prior was, you know, anything less skeptical than this, then you would estimate the, you know, average treatment effect to be positive. So in order to to think that the average treatment effect is like less than or equal to 0, you would need to have a prior like this. And, you know, maybe say something about why you think that prior is, you know, overly extreme, or what would be the reasons to disagree with the sort of necessary prior to disagree with the posterior.
Is there ever a reason where we're working with priors that are far outside? Because like every example that we've done in this class has always been like a reasonable prior. So I don't know like what he was trying to imply, because generally we just use reasonable priors, you know?
Certainly priors that seem reasonable to us. But there's going to be people for which, you know, what you think is a reasonable prior is unreasonable prior to them. And I think, you know, in the sort of from 1995 to 2010 era of sort of first generation of MCMC, there was a lot of usage of what I would call the bugs priors, which are priors that were emphasized by the people who created the bug software, which was really the only general purpose software to do MCMC before Stan. They would do a lot of priors that's like normal with a standard deviation of 1 million. Or, you know, similar sorts of things. If we were talking about something that has to be positive, they would do, you know, something that puts positive or, you know, non-negligible probability on values that are like greater than 1 million. And that was thought to be reasonable. But I think Stan era priors, you know, that's something that would now be considered unreasonable by a lot of people. Like if you're doing a logit model and you're, you know, trying to think about what would be an appropriate prior on a coefficient of like one of those variables for something typical in the social science. If you put a normal prior with a standard deviation of 1 million on, you know, one of those things, well, we know under the normal distribution, like 2/3 of the probability is plus or minus 1 standard deviation. So you're saying, well, there's a 1/3 probability it could be greater than 1 million or less than negative 1 million. But basically the logit or the standard normal CDF overflows to 0 or 1 for any log odds that's like greater than plus or minus 10. Like it's numerically indistinguishable from 1 if you put in a log odds of 10. And so, you know, putting a prior that implies, okay, there's a 1/3 probability this is greater than 1 million, when your computer basically can't even handle values of the log odds that are greater than 10, it's just going to say probability 1. Does that make a lot of sense? No, probably not. One of the ways that I like to think about it was like if you did a regression on the probability of voting for Obama in the 2008 election against McCain, white people had like about 0.4, maybe a little bit less probability of favoring Obama over McCain. But if you just like kept everything about the person the same except changed them from white to black, then the probability of voting for Obama goes to about high 0.9s. And so that works out to a change in the probability of like 0.6. And that implies a change in the log odds of like 3. And that's probably the biggest effect in the history of social science. Like the race effect for, you know, the first major party African-American candidate to ever, you know, be up for election, much less win, you know, against McCain and the Republicans and all that. So what the, you know, largest effect that we can sort of imagine in political science was a change of about 3 in the log odds. but it used to be considered reasonable to put normal like 0, a million priors on regression coefficients in logit models. And so what seems reasonable to one person, or what used to seem reasonable a few years ago, doesn't necessarily seem reasonable to what people are doing today. But I think one of the ways in which you can demonstrate whether your priors are reasonable or not, which we have emphasized in this class and wasn't emphasized that much 10 years ago or so, even though it goes back to an idea of I.J. Good, who was like a contemporary of Turing and, you know, came to the United States and was less subject to the British classification laws on stuff that happened during World War II. Anyway, his idea was, well, draw from the prior predictive distribution and see if the prior predictive distribution is consistent with your beliefs about what you think the outcome will look like. And if you put in 0, infinity, or 0, a million, whatever, normal priors on coefficients in a regression model, and you look at the prior distribution of the success probabilities in like a logit model, they're all going to be like basically 0 or basically 1. And is that a reasonable thing to think about? You know, what's the probability you turn out to vote, or what's the probability you vote like Democrat or Republican? What's the probability that you have a job, or what's the probability you're in the labor force? These sorts of things for, you know, the typical like average sort of person, not having like super extreme values on any of the predictors, there's going to be interior probabilities of success or failure. Otherwise, there would be no reason to really be modeling the thing in the first place, unless you were sort of interested in, you know, shades of gray in the interior of the parameter space as opposed to on the edge. And so I think you can be more convincing as to, you know, these prior beliefs are reasonable or unreasonable by going through, writing down the generative model, being able to draw from the prior predictive distribution of the observables and saying, you know, is this distribution of observables that's implied by my generative model a reasonable thing to think or not? Because I think a lot of people find it easier to reason about distributions of anticipated observables than distributions of things that are fundamentally unobservable and have to just be estimated in the context of a model, like the elasticity of substitution between capital and labor or something like that. Other thoughts on that presentation, that response to it? One of the points that I thought was interesting and probably correct is that, you know, if you do one of these things or any sort of qualitative research, one of the things that there will be disagreement about is whether the clue has actually been found. Like, is the evidence in the historical archives and stuff like that sufficient to say, like, yes, the clue was present, or no, the clue was definitely absent, or, you know, we looked for a long time and we didn't see the clue, but, you know, documents were classified, you know, they got burned up in a fire like 60 years ago, whatever. We might not be able to definitively say K equals 1 or K equals 0. So is that, do you think, an important criticism of the framework put forth by Humphreys and Jacobs, or how would they respond to something like that? How would you respond to something like that?
So just to make sure, your question is mostly about like the limitations of how certain we can be in like saying whether certain qualitative evidence qualifies as a clue. I mean, I feel like that's just the limitations of the scientific process, as much as any one method of doing inference. In some ways, I think Bayesian is helpful because it makes us be honest about, you know, how certain can we be about these things. But I guess you're not really setting priors on like whether a clue is going to give you certain inference. So I don't know. I just feel like it's an inevitable part of the research. I mean, if some archives get burned down, I mean, you've got what you got. You can't just throw up your hands and say we're done. So you've got to come up with some way, you know, to make a, you know, progress in a scientific field. So I just feel like that's more of a limitation of the research process rather than a particular method for me personally.
Do we think that Humphreys and Jacobs framework could be expanded to some sort of thing where we might say, okay, we don't know for sure, but we think the clue existed with probability 0.7 or with a probability distribution that was beta with a median of 0.7? Could we do something like that? Yeah, no reason why not. I mean, basically, the Bayesian, we saw maybe a little bit of that with the climate paper, where their data was sort of the author's assessment of whether these things that would need to be true in order for them to be for there to be a equilibrium climate sensitivity that was like way to the left or way to the right to be true, and they sort of made those assessments. I think there's a lot of connections between that paper and the Humphreys and Jacobs. So they basically had like, you know, subjective data that they were conditioning on in order to get the updated beliefs about what they thought the equilibrium climate sensitivity would be. But, you know, basically the essence of the Bayesian approach is whenever you don't know something, whether that's parameters, the true value of data that you have a terrible measurement on, you know, missing value of data that you don't know, data that might be in dispute, the future, anything. Every time you don't know something, you substitute a known probability distribution. And then, you know, work with that, condition on the information that you have, update your beliefs, update those posterior distributions, and evaluate the implications. And so that actually seems like an interesting extension. And they talk about a number of extensions in the paper, like what if K was continuous, or, you know, what if you didn't do just a simple random sample of the data to look for clues, but, you know, did something else. So there's a lot of extensions that I think could be done sort of within the Humphreys and Jacobs paper. So another thing that I thought was like interesting or perhaps telling about Huber's response was that he sort of referred to priors about like probative values of clues and lambda and all that stuff. So referring almost interchangeably between priors and biases on the part of the researcher. So to what extent do you think that made sense?
I don't know. I found Huber's argument slightly strange. I think, like what you said, he conflated the two. It's almost as if he's made it seem that an objective prior was absolutely possible, like some form of objectivity actually existed. And I think, I'm not sure to what extent his statements was because he didn't understand the framework in which Bayesian statistics is applied, or like how STAN works. But I guess even if you did I mean, there's no one standard where that subjectivity doesn't exist, and there's always a value judgment in making in any academic paper that you're writing. So I mean, it will exist, but what Stan does compare, I mean, you have to compare it against what exists, which is the frequentist method of doing it. And that doesn't really address the issue either. So, I mean, at least in Stan, you can update that with your posterior. But what I was really confused by was Humphreys and Jacobs' response to how the fees can be, like they have 4 methods in which they say like you could address the fees. They have like you either reject, you have conditional statements, you have subjective base, or you have objective base. I was not too convinced by the objective base, because what they said was that the assumption that they're making is that the relationship between clues and types have to be the same across cases. I'm not sure to what extent that would actually hold up. Yeah.
Yeah, I would agree. I think they put some stuff in the paper, like you could do this, that they did not actually favor or really recommend or entirely believe. I don't know to what extent those were sort of added to address things that reviewers brought up. But yeah, like, okay, you could go down the route of like objective priors, like put a flat density on the simplex of lambda, make flat uniform priors on the pi's and the fees. The question is, would you get anything valuable out of the results if you did that with a small number of observations where you go and seek the clues? And that's what I would doubt, and I think probably McCartan would doubt that as well. But yeah, it could be done. In the same way they say, like, you could just maximize the likelihood and not, like, do the Bayesian approach at all. It's also true. But do you get anything worthwhile out of that when, you know, in the examples that they were talking about, and a lot of other examples in social science, there's really nothing particularly frequentist going on. So they do, in their basic models, say, okay, the observations where you go to look for clues, in the simplest case, would be a simple random sample of the total number of observations you have. But there's no sense in which, like, the historical instances of switching from single member districts to proportional representation is a sample of anything, or that we're interested in testing the null hypothesis that, like, the presence of an opposition party is irrelevant, or, you know, other things like that. Maybe it'll become a little bit more clear when we talk about the second problem. But basically, for what I would call like historical data on like revolutions or like civil wars or things like that that people are interested in, they're not a sample. And so there's really no well-defined frequentist inference you could be making on these things in the first place. But no one really wants to. I mean, everybody's interested in saying, like, what is the chances that this hypothesis is true given the historical information, rather than saying, like, what is the probability of observing some weird function of the data, which is not really a sample, conditional on the parameters taking these values. It's a weird way of trying to approach that sort of thing in social science. It might, you know, the frequentist approach be a little bit easier if you're talking about surveys or samples of voters or something like that. But anytime you're talking about institutions or some like important historical episodes, that's not what the frequentist way of doing things was intended to address. That wasn't the questions that was on anybody's mind for attacking with, you know, quantitative research when Fisher was doing his stuff, like in the 1920s and before we had social science, really. So what would we make of qualitative research that, you know, doesn't do the whole other part of the Humphreys and Jacobs framework by sort of combining the 1 or 2 or 10 or whatever things where you investigate deeply and see whether the clues and the mechanisms of, you know, process tracing suggest that the theory might, you know, have more behind it but not combining it with observational, correlational, high volume, relatively low cost data that you can just sort of go out and download, where like at least most of the time, historically speaking, they don't really like estimate anything or necessarily have a model. It's just like, I looked for clues, I found some clues, and then, you know, here's how my idea of how things unfolded would be, you know, supported or less supported by the presence of clues. What can we get out of those sorts of research designs?
For me, I don't think of anything like, parameter estimates. Obviously, they don't even do that. But it's more of like a richer kind of analysis. I also think it's complements the quantitative research. I'm an advocate of the mixed methods framework, where you kind of do a little combination of them, and then you can kind of get on the ground and find fuller, more like, richer things of actually what's going on the ground. So it would be hard for me in political science or economics fields like these to say that progress can be made entirely unqualitative. I mean, you've got to quantify things. I mean, and especially in economics. So I feel like it's more complementary. So I don't know if a body of qualitative research, in my opinion, and again, this is kind of what the talk was addressing, we all attach different weights to different types of evidence, can really on its own lead us to, in quotes, the truth.
Yeah, so I don't think qualitative researchers have been particularly in a rush to adopt this framework and like combine qualitative stuff with more quantitative, observational, high volume, low cost data. There have been sort of a number of papers that have like referred to Humphreys and Jacobs and a more qualitative bent, saying, okay, well, the Bayesian idea of inference applies to qualitative designs as well. It's just how much do we really update our beliefs about things when evidence from only like 1 or 2 or 3 or something countries is presented, even if we have like a lot of interviews and stuff like that on those cases. And so I guess, it's going to depend a little bit, but if you're sort of bringing in like very concentrated information that might not help you sort of speak to more general phenomena in politics or social science, then it's sort of, I think, quite possible in my mind that you're not really updating your beliefs that much when one of these things studies gets conducted, which is sort of fine under the Bayesian framework. But it is, as far as like what it means for the discipline, it basically means that there's essentially a lot of arguments about whose priors are right, because there's not a whole lot to sort of sufficiently update anybody's beliefs to where there's like, more consensus and things like that. So I do think it is worthwhile to try to expand your horizons to incorporate, as much and as from as many sources of information that you can. And so certainly there's a lot that can be done along those lines from data that are cheap to get. Other questions about that? Okay, so I should have made this big. Second question. All right, so these CES models. So we have one like this. And this, I think, is an important question to be able to answer. There's been, a lot of concern over the semester of, whether you got things, right or whatever on the third homework, or, can I take it pass fail because this is going to be adversely affecting my GPA too much, or things like that. That is, less central to the question of, can you do a Bayesian analysis by the end of the course, which is really what, the learning objective for a class like this is. And, this constant elasticity of substitution model, it's not like literally the simplest non-trivial model that is actually used in macroeconomics, but if you restrict sigma to be 1, then you have Cobb-Douglas, and that literally is the simplest non-trivial macroeconomic model that is, or still is, but certainly was used in research. And so, to what extent can you credibly claim to be, qualified to apply quantitative methods to the social sciences if you can't estimate a sort of relatively simple, just how do capital and labor combine to imply the level of output model? But one of the things that I think you can't do is take a frequentist approach to a question like this. Of course, that's exactly the approach taken in that vignette that supplies this function for estimating models like this. And it's certainly how, if you look up the millions of citations of like solo models on Google Scholar or whatever, all the empirical stuff has been frequentist. But it doesn't actually make any sense to do so. And so if you've only been trained on how to apply frequentist methods, then you're not really in a good position to approach empirical estimation of a function or a model like this. So what are the reasons why the frequentist approach is not adequate? Well, it's not a sample. It has like 92 countries in this particular data set. And all of the quantities that you get with standard errors and p-values and confidence intervals are all about, well, what if there was another sample of 92 countries that was drawn from the same population as this? How much would we expect the point estimates to differ or whatnot? There aren't another 92 countries that had data on the value of the capital stock and whatnot from like 1960 to 1984, whenever the data stopped. Those like 92 countries in the data set being used are the only ones that we have. So there's no, what if there was another sample that was like this? What has happened in this situation is one that happens in a lot of situations when doing research, where the original researchers who collected these data just said, well, give me all the readily available data. So there's no sample, there's no well-defined population, there's no prospects really for getting other countries' data from this time period. So all of the questions about the distribution of an estimator across samples that could be drawn from this population are basically moot questions, because this is the population, at least the population with which we can get data. If you look at the vignette for that package, yeah, they do a lot of frequentist stuff in terms of like the options that they present to estimate the thing, but they're not actually interested in making any frequentist inference. Like, what would a null hypothesis that you might test be in something like this? Are you going to test the null hypothesis that the stock of capital has no effect on output? That's already been rejected by anyone with half a brain. So what value is you coming up with some calculation of a p-value that's like 0.0000 for a null hypothesis that nobody believed in the first place. So what these things about are really about like estimating the parameters. Maybe like, is sigma close enough to 1 that we could go away with a simpler Cobb-Douglas form of the model, sorts of things like that. Rather about testing a hypothesis about a particular value. Moreover, although like the homework problem didn't ask you to do it, this is a classic example where you would probably want to be doing a multi-level model rather than a flat model, allowing for the sigmas and the rho and the other stuff maybe to vary a little bit from one country to the next, or one region, or like types of countries in the development stratification, to differ a little bit, instead of assuming that sigma is constant for every country throughout this time period. And that would sort of naturally lead you to Bayesian estimation rather than frequentist estimation. Because if you try to do a frequentist version of a multi-level model like this, you would almost certainly have a big probability of getting corner estimates and all sorts of other things like that we talked about on the previous homework. So the frequentist approach is really not adequate. And even though the other package that provided these data and this estimator was like very, very frequentist, they didn't actually say why they were doing it that way. It's just, that's the way it's always been done. And that's the way that like 97% probably plus economists are expecting it to be done. But there's no actual reason for that. And if you read like the rest of the vignette, which I said you didn't have to, it was all about, well, here's 10 different ways that you could like try to find the optimum, which turns out to be really difficult. But that's a problem that they brought on themselves by choosing to do optimization to obtain point estimates of the parameters instead of using sampling from the posterior distribution to get a distribution of beliefs about the parameters. And one of the things that it sort of manifests itself with is that people who do frequentist estimation are really only concerned with, is the point estimate admissible? Not, okay, here's my uncertainty around a point estimate or, posterior mean or something like that. And, does the uncertainty implied by the estimator go into the non-admissible region of the parameter space under the model? And that's where, I guess, if we pick it up, you take the logarithm of this thing, it works out to be, expression like this. So you have logarithm A plus 1 over p times log of 1 minus alpha minus 1 over rho times log of 1 minus alpha to this covariate raised to the power negative rho. Okay, so we know that sigma has to be positive. That's it. Elasticity of substitution between like the capital part and the labor part. We know that alpha has to be between 0 and 1. And so, these are things that are relatively easy to specify, those sorts of constraints in Stan. But the frequentist, like just minimize the sum of squared errors, doesn't impose those constraints. They just get the solution that minimizes the sum of squared residuals and then see if it satisfies those constraints, the point estimate, without worrying too much or even at all about, okay, well, if we had some uncertainty, does the uncertainty go out of the admissible region of the parameters? And if so, it's not really uncertainty because we're certain that alpha can't be greater than 1. And so if you got like a confidence interval on alpha that poked out above 1, we would know that doesn't, reflect reasonable beliefs or whatnot about those. But there's implicit constraint on this, that thing you're taking the logarithm of has to be positive, or else the logarithm is not going to be a real number. And that means basically that alpha has to be sufficiently close to 0 that all of the x2 raised to the power negative rho, you know, when you multiply that by alpha, it has to be less than 1 in order for 1 minus that to be positive. So it's not merely the case that alpha has to be less than 1. Alpha has to be close enough to 0 so that logarithm thing is real. And that's another thing that's sort of, you know, pretty obvious about our beliefs if we're going to use a model like this, but isn't being imposed by frequentist estimators. And you need to impose it when you're doing this sort of thing in stands. So we need to give an upper bound on alpha to make sure we're not taking the logarithm of any negative numbers. And that upper bound on alpha is going to depend on what the data on X is and also on what rho is. But that is something that we can do in Stan. I think that's not something that we've done in Stan previously, but it's something that you should at least have been, you know, encountering if you know, tried to do that without, and you'll, you know, get an error message, something about trying to take the logarithm of a negative number somewhere along the way that should have pointed you on the path to doing something like this. So if you look at the code, you know, pass in the exogenous knowns. That was something that some people were a little bit confused on. And then before getting into the rest of the SBC stuff, I calculated the maximum and the minimum of the X2 thing in order to figure out some bounds on alpha. So you could use, you know, whatever priors you want on these sorts of things. I think there's something of a belief among economists that sigma is close-ish to 1. So rho is kind of close to 0. You could either parameterize this in terms of rho and make sigma endogenous unknown, or you could parameterize it in terms of sigma and make rho the endogenous unknown. Because there's a one-to-one transformation between sigma and rho, you can do it either way. It's probably a little bit more natural from the perspective of economics to do this in terms of sigma because that's the elasticity of substitution, whereas rho doesn't have like any particular interpretation. But this is what I was talking about on alpha. A lot of people were doing sort of uniform between 0 and 1, and they were getting all these error messages from SBC and didn't know why. Well, I think there may have been multiple reasons why, but one of the reasons why you might have been trying to take the logarithm of a number that could be negative depending on what value of sigma you drew from your prior. And so we can put the upper bound, instead of being 1, put it as like the reciprocal of the most extreme value of x2 raised to the power of rho. And so if rho is less than -1, then negative of like -2 is going to be 2. And so values of x2 that are greater than 1 are going to get squared up. Whereas if rho is like between 0 and 1 and you take the negative of it, then values of x2 that are close to 0 are going to get blown up. So you have to check both on the low side and on the high side. But if you set this so that the upper bound on alpha is equal to the reciprocal of the most extreme value of x2 raised to the power -rho, then you've ensured that the quantity that you're taking the logarithm of is going to be positive. And you would avoid those error messages. Also prior on the standard deviation of the errors. So a lot of times in economics, you'll just see them present like a deterministic model, but nothing in social science is deterministic, certainly not macroeconomics. And so it makes sense to introduce an error term, whether that's due to measurement error in GDP or unexplained factors that go into that are not explained by the model, we need one of those going around. And then given these draws from the priors, we can then obtain conditional mean and draws from the prior predictive distribution and then condition on that data from the prior predictive distribution in order to update our beliefs about the parameters, but we should not be able to systematically change our beliefs if we're conditioning on data that is drawn from the model, but propagating our uncertainty about the parameters and the observations through. So we have all of these parameters in the parameters block that correspond to the things in the transform data block. Again, we need to be putting an upper bound on alpha to make sure this logarithm is real. But then, we go basically the same process in the model block, except instead of thinking about drawing independently from a normal distribution, exponential, something like that, we need to build up the numerator of Bayes' rule in terms of log units for all these densities. So we have a log likelihood contribution from y given mu, the conditional mean that we built up. And then we have priors on, the log A, the elasticity of substitution, standard deviation of the errors. And then if we don't put anything else, and it would probably be hard to do that convincingly, we're basically saying our prior on alpha is uniform between 0 and its upper bound, but the upper bound depends on the proposal for sigma. And then in the generated quantities block, we can calculate some extra stuff like A and delta, which are just functions of our parameters. And then the stuff we need for SBC, like copy the parameters, see if this is bigger than that, calculate up the log likelihood contribution for each observation so we can do Pareto K sensitivity, all the things that we sort of talked about. So questions about, you can look through the details, and if your priors were different, then the results are going to be different, and also like how you might set it up is a little bit different. But is there any questions about like what it is I was trying to do with my code? Yes.
The purpose of y underscore in the generated quantities, because I realized it wasn't used in the code, but then if I remove it, actually the code runs faster.
Maybe a little bit. It's just if and when you have problems, you might want to look at that distribution of prior predictions. So maybe it's predicting like GDP per hour worked of like $100,000 or something, that's inconsistent with everybody's beliefs. So you might want to look. So ranks is used to make that plot. Pars is not actually being used. You just make a copy of the realizations from my prior so I can see if that looks weird, but also make a copy of the prior predictive distribution so I could dig into that more if I thought I was encountering problems. Maybe my priors combine in some way that yields an implausible distribution for the predicted outcomes. So yeah, that stuff is there. It just doesn't appear in the output. So you could run that. You might get, some of the 500 runs or whatever might just like totally fail, like you get an error message. So if there's too many of those, you would want to be suspicious, but you can probably like get those to a small number if you just sort of tweak the settings or the initial values or something like that. I had to do this a few times because I was getting some divergent transitions when I ran it. So it had to make adapt delta pretty large, but then didn't have divergent transitions and didn't really have much of a problem with particular observations being overly influential. Did you get something way different? You had a lot of divergent transitions. Yes, with the default value, which is 0.8, I had a lot of divergent transitions too. And that's telling you, okay, the posterior distribution that tends to be produced by a model like this has severe curvature at some parts of the parameter space. And so if you're going to do this in Stan, you have to go through with smaller steps to not miss anything. But okay, that's a problem, but it's a manageable problem. What's not as promising is the histogram of stuff that you get out. So log A and sigma y, those seem fine. But there's a marked tendency to overestimate y and or sigma and alpha. So missing parts of the posterior distribution could be some bimodality. You'd have to dig into it a little bit more. But one thing you might hope is the case that this distortion is hopefully driven by more extreme values of alpha or sigma that might not have a whole lot of probability under your priors, or maybe your priors need to be more informative to reflect what you actually believe. But for the priors that I use, like exponential one and uniform and stuff like that, ran into evidence that this is going to be problematic for Stan. And if it's problematic for Stan, it's going to be even more problematic for any other Bayesian or probably frequentist estimator as well. So that would be more stuff to look into. And then maybe think about reparameterizing the model, generalizing the model to allow for multi-level structure, changing the prior, something like that. But we could go ahead and estimate it, or that's at least what the problem said to do. Just comment out all the stuff that pertains to SBC, move the endogenous known up into the data block, pass it from R rather than simulating, and all the rest is the same, like the parameters block and the models block for calculating it. And you go to do this, and you get back posterior means, at least, that are reasonably precisely estimated, definitely well into the interior of the parameter space. So it may be the case that for these particular data, maybe the problems that you saw from SBC might not be as severe or as applicable for these particular observations, but there is a high probability of getting realizations from the prior predictive distribution that would be problematic in terms of estimating the posterior conditional on those. So perhaps these data are way more auspicious than the typical data that'd be drawn from a prior predictive distribution. Of course, there's not that close a connection between these posterior means and the point estimates that you would get if you do like the frequentist thing, but there's no reason to really think that there should be, because that's just a mode of something that has no restrictions or prior information about it at all, and only has asymptotic justification and all these other things that we have talked about versus the Bayesian approach. And so if you look at the pairs plot, there's nothing particularly striking going on, but there is a very high negative correlation between sigma and alpha, which isn't problematic in and of itself, although this is probably the reason why we had to make adapt delta high enough in order to go through like something that's highly correlated like that. But you could understand why you know, the estimates of sigma and alpha would tend to be, you know, if one is wrong, the other are highly wrong when you do it with the prior predictive distribution. So hopefully you got something somewhat like that, but I don't think it would correspond that well to what CES produces. Of course, if you look at the documentation of that, it basically says like there's no reason to trust this function because it's hard to get to the optimum, and even if you get to the optimum in finite number of observations, particularly observations less than 100 or whatever, there's nothing particularly useful about that one point if it's not like a very smooth, like normal looking, you know, you can get all the uncertainty just by evaluating the curvature at the mode sort of deals, which it's not in this case. And honestly, it tends to not be for problems that were first posed after Fisher's heyday. So maximum likelihood works decently well, has, you know, good frequentist properties in finite samples, is pretty close to the Bayesian posterior mean, posterior mode in finite samples for problems that are so simple that Fisher could attack them in the 1920s, like estimating a mean or like least squares or other things that were like known back in 1920, 1930. For these like slightly more recent things that came along like after 1950, and you have this nonlinear relationship between the predictors and the conditional mean, that is the sort of problem that maximum likelihood tends to not work well in reasonably sized finite samples, even on frequentist grounds, much less on Bayesian grounds. Questions about that? Yes.
Do you have any suggestion on how to choose the prior, like the distribution form or the range?
So in order to do this actually well, you would need to have some background in the literature on these things, which I realize not everybody necessarily had. So if you had, you know, read more about like many studies that have done something like this, there's, I would say, a rough consensus that sigma, elasticity of substitution, is not too far away from 1. So you might want to have a prior like I did, whose prior mean is 1. Okay, that could be kind of reasonable. Also need to be thinking about the units. So growth GDP 85 is like, I guess, GDP per hour worked. So that's going to be something along the lines of like what would be the average wage in that country if the economy was all like working smoothly. So the logarithm of that is probably going to be a positive number, but it's not going to be like a super big number. So you can think about like what is a reasonable range for the outcome when thinking about what would be reasonable scope of uncertainty for the priors. But in order to do this actually well, in order to maybe tighten up the priors so we wouldn't have, you know, a problematic region where we were, you know, tending to overestimate things and things like that, you need to think about the substance of the problem. But that's an opportunity, you know, if you're doing like the Humphreys and Jacobs thing, to put your prior information about the probative values of clues, or to put your, you know, consensus beliefs that macroeconomists believe about elasticity of substitution in the model, as opposed to just say, okay, we're going to get the mode and see if it's within the reasonable region of the parameter space, and not really worry about, okay, well, there has to be uncertainty around that mode. And is that uncertainty of plausible values combined to the admissible region? It's usually not, which is why you have to sort of impose those constraints explicitly when doing something like that in standard. Okay, So moving along to the rest of the stuff for today, we'll probably have to go through it pretty quick. We want to talk about multiple imputation of missing data after we talk about the fact that we're still at Columbia. Columbia is still developing STAN, still seeking grants to develop STAN, still using STAN outside Columbia, and still have an appearance of a conflict. So when we ended up last time, we were talking about some prior predicted distributions that also had a missingness mechanism, a process by which some observations come out in A and some come out as actual numbers. And so you have like a regular sort of prior predicted distribution for the true values. And then you have some Bernoulli-ish process by which, you know, if this comes up success, then the thing goes missing. And if it comes up failure, then you get to actually observe the number. And just by factoring the posterior distribution, if we consider the fees, so the parameters govern the missingness mechanism, and R, which is like a Bernoulli 0-1 matrix that indicates whether the observation is there or not, we could, you know, factor things around to draw from the posterior distribution of the missing values, and then compose that with a conditional distribution for the parameters given both the observed and the missing value. And that is really the rationale for what is considered the most rigorous approach to dealing with missing data, even though I don't think it's all that good. Where what we do, or what was proposed doing, and again, this goes back to like the 1970s, before there was MCMC or anything like that, Don Rubin, who's Bayesian, but was sort of addressing surveys and educational research and other things that had no idea how to apply a Bayesian sort of framework to missing data problems, said, well, you could draw a bunch multiple times, m times, from a posterior distribution of the missing value, missing data and phi, conditional on the observed data and R. And if you had like m draws from that posterior distribution, you could take all those draws and fill them in to your data set where the as they corresponded to on the missing values, and you would have m what's known as complete ed data sets. Not complete, because some of the data were originally missing, but if you just sort of take the original data set and put in different posterior realizations for the missing values, then you could stack those up and you'd have m completed data sets that you could apply some estimator to, in particular a frequentist estimator to, and then, you know, apply that as if there was no missingness to begin with, and then you would get m point estimates that you could then average together or do some other things in order to get like a single point estimate. So multiple imputation, that's what this is describing, is a two-step process. First, draw from the posterior distribution of the missing values, take each of those m realizations from the posterior distribution of the missing values, fill in your original data set wherever the observations were missing, and now you have m complete ed data sets. You do like least squares or maximum likelihood m times, get m sets of point estimates, and then average them together. And that is an estimator that actually has decent frequentist properties. Moreover, it's easy to convince frequentists that they're applying a frequentist estimator, but it's actually Bayesian, because basically your frequentist estimator is like a generated quantity. You're taking the posterior distribution of your frequentist estimator and averaging it over your uncertainty as to what the true values of the missing values were. You're just not propagating through all of the uncertainty that you would if it was like a full Bayesian analysis. but at the heart of it, it's Bayesian. So in practice, when people do multiple imputation, they're almost always assuming the data generating process is missing at random, which is to say conditioning on R doesn't give you any information about the missing values, so you don't need to do it. And instead of like explicitly doing drawing for the posterior distribution, it's usually some approximate posterior distribution thing that they're drawing from, and doing other, shortcuts that they had to do before there was stand, but honestly, there's not a whole lot of appetite for doing anything particularly complicated in order to get draws from the posterior distribution of the missing values. So I pretty much already said that. Let's see how we would do something like that in stand. So you may have heard of Amelia, which is like an R package and a Stata package for doing imputation based on a multivariate normal distribution. There's similar algorithms in SAS and a bunch of other programs because this is fairly easy, and it's something that you could do yourself with the following stand code. So we have total number of observations. They were originally intended to be collected on K variables. We have this R two-dimensional integer array that's n by K, 1 if the thing was observed, 0 if the thing is missing. And then we just make like a long vector of the observed values, just flatten it, concatenate it to one dimension. And that's our endogenous but known. So basically, if you have missingness on any variable, that variable has to be endogenous because you need some way of predicting the missing values on it. So if we just say, okay, we're going to use multivariate normal, like all of the variables are endogenous sort of thing. Then in the parameters block, we also declare a long complementary vector for the missing values. In addition to the mean and the Cholesky factor of the covariance matrix of this multivariate normal that we're using to model the data with. And so we have this long concatenated vector of observed values that came from like different parts of our variables. And then we have also long, but vector xm for the posterior values of the observations on different variables that were missing. And if you put xo and xm together, the total length of that is going to be n by k. So we have one value for each cell in our data matrix. It could have been observed, or we could be drawing from the posterior distribution of it. So what we do in the model block is we create this n-dimensional array. Remember, those are like a list of row vectors of size k. So we have basically a list of row vectors of size k, and the length of that list is size n. This is x sub c for the completed data. And we're going to loop through that over all the observations and all the variables. If the thing was originally observed, we're going to put into the ith row, basically, and kth column of x sub c, the data that we observed, or the data point that we observed. And then we sort of do that, from the front of that xo vector to the back, incrementing up this obs mark thing to keep track of where we were. So we use like every data point that was observed exactly once. If our I comma k was 0, not 1, then we pop off from xm, which was declared in the parameters block, and we stick that into the appropriate place in x sub c, and then increment up our placeholder for where we are in that vector of true values when the data was originally missing. And so when we go through both of those loops, x sub c has been fully filled in. It's like an n by k structure. Some of its elements were observed from the data, and some of its elements came from, proposals from the posterior distribution with the usual Hamiltonian Monte Carlo mechanism. And so then it's just multivariate normal likelihood on X sub C with mean vector mu and Cholesky factor of covariance matrix L. And if we were doing this in the Bayesian way, we would want to put priors on mu and L and any other parameters that we might have. But basically, we're using this multivariate normal as likelihood contributions when the data are observed, or prior on the missing values when they're not observed. It's the same multivariate normal distribution either way that we think is governing the true data generating process. But if you didn't have priors on mu and L and you just did like a maximum likelihood or something like this to get point estimates of mu and L, that's basically what Amelia is doing. But that is something that you can do for yourself and you can improve upon if you were doing it in Stan. So I generate some like 100 by 5 data with some missingness using the same function that we had on Thursday. Then I calculate, number of rows, number of columns. I make my R matrix as to whether, X is NA or not. Then I sort of extract out into a long vector all the actual observed non-NA values in XO. And whatever is the length of that. Pass that in the list of data to the data block of Stan in the previous one. So this is multiple imputation underscore MDN.Stan. And then I run that. There's an extract function in our Stan where you can get out the posterior distribution of like particular elements of the parameter space as a list. And so I had in my 100 by 5 data matrix, 24 of those values were NA. And now I have a 4000 by 24 matrix of posterior draws on all those missing values. So I could just like take those 4,000, or honestly a subset of those 4,000 would probably be more than adequate, and then stuff those posterior realizations into my 24 places in my data set where I had an NA, and do that M out of the 4,000 times. M is often like 5 or 10, honestly, but it couldn't hurt to be 4. But anyway, take like M rows of this matrix and the 24 columns, replace the NA in your original data set with that realization from the posterior distribution. Now you have M data sets that you can do whatever you want with, and they have no missingness anymore because you've replaced the missing values with draws from the posterior distribution that you got from Stan. You could do any frequentist or actually any Bayesian estimator on those M data sets. From those M data sets, just average the results at the end. And then you have so anyway, you could certainly do that in Stan, and if you were to do that in Stan, there's a lot of things you could do that would make this better. You could reparameterize it so it was easier to specify priors on things. You could do multivariate normal, so the mu, or multi-level model, so mu wouldn't necessarily be exactly the same for every observation, but could differ from one country to the next, or one state to the next, or something like that. You could model the missingness mechanism. So rather than assuming it's missing at random, you could assume it's missing not at random. In which case, modeling R as like a sequence of logit models or whatever gives you additional information about the posterior distribution of the missing values. So if it's the case that people with high income are less likely to report to you in the survey what their income is, the fact that they were missing affects your beliefs about what the true value that went missing was. And that gets you a more precise set of posterior beliefs about what all these missing values are. So I had a few more things, but we're not going to have time to cover those. It's probably more important to talk about the homework. Monday is the end of the semester. We will have a review session like at 4-ish on Tuesday afternoon of next week. It won't be in here. It'll be in IAB 270B in the basement in the conference room in there. So we'll have a chance to review a lot of stuff then, but definitely come prepared with questions. I will put some more review questions up on Canvas that we can also talk about. More of the sort that might be on the final than some of the problems that we've done for the homeworks. The final is the Tuesday after next. It also will be in the afternoon. It also won't be in this room. I think it's in IAB somewhere. But that information is on the registrar's website. They gave a link to it on CampusWire. So anyway, main thing, review session on Tuesday, but that's sort of during the meeting period rather than the actual semester. So we won't have any new material for then. We'll just be going over old material and also maybe talk about some of the questions that might be on the exam. So you'll probably want to make sure you can be there for that, but whether you can or not, be sure to keep asking questions on CampusWire about things that you're still not clear on as you review and stuff for the final exam. Honestly, a lot of you have less participation on CampusWire than some of the NYU students, even though they've only had half as many weeks as we've had for the semester. So that is another opportunity to get a discussion going about the things that you're still unclear on as you study more for the final. So that is it. Well, that's it for official part of the semester, but still ways to go, I think, in terms of getting everybody prepared to do the final, but more like practically to be able to do these sorts of Bayesian techniques, you know, after the final, which is really more like the goal for a class like this or for the QMSS in general than, you know, scoring points on assignments, finals or anything. Okay, so I will see probably as many of you on Tuesday. I won't have office hours on Tuesday, but I will have office hours some other time next week. Come in and talk about more stuff.